As I told you before, most of the operations on a binary search tree run in logarithmic time. But this happens only if the tree is balanced. In a balanced tree, the difference between the height of the left and right subtrees of every node should be less than or equal to 1. In other words, we cannot have a long branch. Let's look at a few examples. This is what we call a perfect tree. Every level except the last level is full of nodes. Now, in reality, our trees hardly look like this. As we add or remove values, some branches get a bit longer. So they look more like this. This tree is balanced because the difference between the height of the left and right subtrees of every node is less than or equal to 1. However, if we add a new node here, this tree becomes unbalanced. The right subtree is taller than the left subtree by more than 1. Here's another unbalanced tree. This is called a right-skewed binary tree. In a right-skewed tree, most of the nodes only have the right child. We also have left-skewed binary trees, in which most of the nodes only have a left child. These skewed trees are actually the worst types of binary search trees. In fact, they're not trees at all. They're like linked lists, where every node references the next node. If the value we are looking for is in the last node of this tree, we have to traverse the entire tree to find it. That's an O of n operation, just like searching for an item in a linked list. Now you might ask, how do our trees become unbalanced? This happens when we insert sorted values in them, either in ascending or descending order. Here's an example. We want to add these values in a binary search tree. We add 7 at the root. Now we want to add 10. 10 is greater than 7, so we should add it on the right. Next, we want to add 15. Again, 15 is greater, so we should go on the right as well. By the same token, 20 and 25 will end up on the right side. Now we have a right-skewed tree. If our numbers were sorted in descending order, we would end up with a left-skewed binary tree. Now here's the thing. Even if our numbers are not sorted, binary search trees can still become unbalanced. But the good thing is that there are different algorithms for balancing trees. AVL trees are the first self-balancing trees introduced in the 60s. They're named after their inventors, Adelson, Velsky, and Landis. They're actually a special type of binary search trees, but they have a self-balancing property. So every time we insert or remove a value, the tree rebalances itself. Now, AVL trees are not the only self-balancing trees. We also have red-black trees, B trees, splay trees, and so on. You don't really need to learn all of them unless you're really passionate about the topic. They don't come up in interviews, and I would say most software engineers out there are not familiar with these other types of trees either. So in this section, we're going to focus entirely on AVL trees because they're easier to understand. Next, we're going to see how AVL trees rebalance themselves.